How to handle overlapping clusters in machine learning. Imagine trying to sort a box of mixed candies where some pieces fit into more than one flavor category. That's similar to what happens with overlapping clusters in machine learning. It's a common challenge when data points naturally belong to multiple groups. In real-world data, overlaps happen often, like a person fitting into multiple customer segments or a gene involved in several biological functions. Handling these overlaps requires special methods that allow data points to be part of more than one cluster instead of forcing a single assignment. One way to do this is through soft clustering methods. Instead of saying a data point belongs to only one cluster, soft clustering assigns probabilities for each point to belong to multiple clusters. For example, fuzzy C-means is a popular algorithm where each data point has a degree of membership to different groups. If a point has a high probability for two clusters, it's considered overlapping. You can set a threshold to decide when a point is part of multiple clusters. Another approach is using models explicitly designed for overlaps. These models, like the K-extended method, allow points to belong to several clusters at once. They try to minimize the distance from each point to multiple cluster centers, balancing the memberships. Sometimes, constraints are added to limit how many clusters a point can belong to, which helps keep the results understandable. Density-based clustering algorithms like dbScan and optics are also good at handling overlaps. They focus on areas where data points are densely packed and can naturally identify clusters that overlap or have irregular shapes. These methods don't force a point into just one group but instead look at local data density, making them flexible for complex data. Probabilistic models such as Gaussian mixture models also work well. They assume data points are generated from multiple overlapping distributions. Each point can be associated with several components, reflecting overlaps. These models often need careful tuning, like setting thresholds for memberships, to get meaningful results. Graph-based methods are another option, especially useful in social network analysis or bioinformatics. They build graphs where nodes are data points and edges show similarities. Overlapping communities or clusters are then detected as groups sharing many connections, which naturally allows overlaps. Choosing the right technique depends on your data and what you want to achieve. For example, in natural language processing, words often belong to multiple topics, so overlapping clusters make sense. In bioinformatics, genes can be part of multiple pathways, so models that allow overlaps give more accurate insights. Incorporating domain knowledge, like limiting the number of clusters a point can belong to, helps make the results clearer and more useful. Handling overlaps in clustering aligns with the goal of building models that mirror real-world relationships. Whether you're working with text, images, or biological data, these methods help you find meaningful groupings even when data points belong to more than one category. This flexibility makes your clustering more realistic and applicable to complex data.